Okay, yeah. So the title is a bit weird, and the good point is that I'm going to talk about the same things as what Francesco was talking in the first talk, but also about the same things as what Roman was talking in the second talk, more or less. I'll try to convince you that this is actually more or less the same thing. So understanding convex. Manifolds from their boundaries. Thank you. Great. So, first, I'd like to remind you of the Vibe problem, and of course, this is really a bad idea because Roman just explained almost everything about it. I'm just going to repeat it anyway, right? So the Vibe problem in Euclidean space, that's a very classical question asked by Hermann Weyl, and it leads to the following theorem, which is a theorem proved by a number of people, and I'm not going to remind you of all the names already mentioned by Roman. I think there was Levy. I mean, a number of people. So the statement is the following. So I'm going to take H, the smooth metric. This is going to simplify things for me, but we could take something else. It's a smooth metric on S2 with curvature bigger than 0. Okay, bigger than 0. Then there are different ways to state it, but I'm going to state the result in one way, and then we're going to see another way. There exists a unique omega in R3, which is a convex subset with smooth boundary, such that the induced metric, and I'm going to write 1 for the induced metric on the boundary of omega, is isometric to H. So 1 is what people classically call the first fundamental form. This is the reason why I use 1 for the induced metric. Yeah? And then the first question you can ask if you're a hyperbolic geometer is, what is this going to become in H3? So in H3, so basically there are similar statements. And basically there is one due to Alexandrov and Pogoryelov. And I'm going to state it here. And actually, I think this was also stated by Roman. I think it's actually in this statement, it's in this way, it's really Alexandrov. So it's the same situation. So I'm going to take H, the smooth metric, but now on S2 with curvature bigger than -1. And the conclusion is that there exists, well, I'm going to write it in a shorter way, there exists a unique omega in H3, convex, and I would say bounded domain, with smooth boundary, such that the induced metric 1 on the boundary of omega is H. Yeah, so it's a very nice theorem from the 50s, I guess. Yeah. So that was first statement. And then the remark is that there is also a polyhedral version of this. Also by Alexandrov, and it actually came before the smooth statement. And this is now for H, a hyperbolic metric with cone singularities in the way explained by Roman. And I assume that the angle at every singularity is less than 2 pi, with total angle theta less than 2 pi. So this corresponds to curvature, singular curvature bigger than 0 at all cone singularities. That's a nice, very nice theorem. Is this clear? Yeah. Okay. Now I would like to explain that there is a dual statement, and everything I'm going to say in this talk, it always comes in two versions. There is a version like this, and then there is a dual version. And the dual statement involves the third Fernand form. So I'm going to recall that if you have a surface sigma in H3, then you can define its shape operator, B. So that's a morphism from the tangents of sigma to itself, defined by the fact that Bx is minus dxn. This is the connection of H3, the Vichy-Beta connection of H3. And then I can define the third Fernand form of sigma by the equation that sigma on x and y, or x and y, is the induced metric on dx, on bx and by. Yeah. So what this third Fernand form does is it basically measures how much the normal vector moves when you move along the surface. Yeah. If you have a surface which is totally geodesic, this object is 0, and if it's curved, then it becomes big. Yeah. Any question? No, Mark? No? Okay. So now I'd like to state a theorem which is the dual Alexandrov test statement, which is something actually I did in my thesis in 1996, I guess, a few years ago. And the statement is the following. So let now H star be a smooth metric on S2 with now I have two conditions. The first condition is that the curvature is less than 1. And the second condition, I'm going to write it in a shorter way later, is that all closed geodesics of H star have curvature, have length, bigger than 2 pi. Yeah? So the conclusion is that then there exists a unique omega in H3 with the third Fernand form on the boundary equal to H star. Yeah? So one remark, which doesn't play a role here anyway, is that those two conditions together, they really go together well, and together they say that the metric H star is cat1. That's really a natural way to put those things together. And then I'd like also to remind you that there is a theorem of Hodgson Riemann that says exactly the same thing. So that's earlier, 1986. Same for polyhedral in H3. And then what you consider is that the third Fernand form is replaced by the dual metric. The dual metric, I'm going to explain what it is, which is a spherical cone metric. With cone angles theta I bigger than 2 pi at the singularities. And this condition that the lengths of closed geodesics are all bigger than 2 pi. Yeah? So what is this dual metric? Well, I'm going to try to draw a bit what it is. It's really the limit of this third Fernand form if you approximate a polyhedron by smooth surfaces. And the way you can define it is the following. You can define it in the following way. So you have this, polyhedron. At every vertex, you look at the set of orthogonals to orthogonal to the support planes of the polyhedron. So this gives you a little, cone, and you take the projectivization of this cone, so the set of unit vectors, and you can realize that you can glue the cones corresponding to different vertices. The reason you can glue the cones is that the cone here has an edge corresponding to this edge here, and with length of this edge equal to the exterior dihedral angle here. Yeah, so it will be the same here, and you can glue those things. I'm really bad at drawing things, I'm sorry. But you can glue those spherical cones, and you will get this dual metric. Yeah? Huh? Yeah, no. Let's talk about it later. It's true that this Hudson-Riemann theorem is an extension of the Andreev theorem for compact polyhedra in hyperbolic space, which describes the same result when the cone angle, where the dihedral angles are less than are acute. So the angles are less than pi over 2, or the exterior angles are bigger than pi over 2. And it happens that in that case, there is a combinatorial description of the possible metrics, and this corresponds to the dihedral, to the Andreev theorem. But I prefer to forget about it. Okay. Okay, so now I'm going to keep those things on the blackboard because the goal of my talk is to try to understand how those things will be extended in other settings. I'd like to make a remark, however. So maybe I should give names to theorems. So this theorem here, I'm going to call this theorem 1. And then basically this theorem, let's call it 1 star. Okay, now I clearly messed up with the blackboard, so I'm sorry about that. I should do this differently. Now this works. So there is another way to state theorem 1, and I think it's very relevant, and hopefully I'm going to try to show you that it's relevant to think of it too. So theorem 1 can also be written in the following equivalent form. And the statement is now, again, take H be a smooth metric, the same hypothesis on S2 with curvature bigger than -1. Then there exists a unique immersion phi from S2 into H3 such that the induced metric of the immersion is H. Yeah? So the question is, why are those two things equivalent? And the reason is that if we have an immersion, I should say a smooth immersion, if I have an immersion so that the induced metric has curvature bigger than -1, then this immersion must be locally convex. And if I have a locally convex immersion of the sphere into H3, it must be an embedding, and it must be, the image must be the boundary of a convex domain. Yeah? So those two things are really equivalent. There are two ways to state the same things. And in the same way, theorem 1 star has an equivalent form. So again, I take H star, the smooth on S2 with curvature less than 1, and this condition on the length of geodesics, which I'm going to write just L bigger than 2 pi. So all closed geodesics have lengths bigger than 2 pi. Then there exists a unique smooth immersion phi from S2 into H3, such that the third fundamental form induced by this phi is H star. Yeah? And this is again, a consequence, because for the same reason, if I have a smooth immersion, such that the third fundamental form has curvature less than 1, then this must be locally convex, therefore it must be an embedding, and the image must be the boundary of a sphere. Okay, so now the question is, how can we extend those statements to more interesting statements than just the boundary of a convex domain? And there are different ways we can do that. I'm going to try to do two things. First, add some topology, and then I'd like to go to the universal setting for this problem. I'd like to convince you that there are some things to do and also many questions. So the second state settings is convex hyperbolic manifolds. And by this, I really mean exactly what Roman was talking about. I'm going to give you a definition. I'm going to say that really non-complete hyperbolic manifold, three-dimensional manifold, M, is convex if any path between 2 points x, y in the interior of M can be deformed with fixed extremities, endpoints, to a geodesic segment. A geodesic segment in the interior of M between the same endpoints. So I'm fixing the endpoints in the deformations. Yeah? So the key idea is that, of course, those things are intrinsically defined. But when you have this definition, you can always embed this manifold in a bigger and actually biggest hyperbolic manifold containing it. That's the following remark. So given such an M, there exists, and it's unique, unique under some conditions, there exists a complete hyperbolic manifold MX. X could be extension or it could be extremal, because this is extremal in some sense, containing M isometrically. So in which M embeds isometrically. So basically, I don't want to really talk too much about general things. The case I'm really interested in is the case of what I'm going to call quasifuchsian manifolds. And that's the simplest case topologically. And what I'm going to say in the rest of the talk is usually can be extended to more general situations, but just understanding this one is already not bad. So I'm going to take M, take a surface cross -1, 1. And then I'm going to assume that my manifold, my convex manifold is something like this. So it's the product of a surface by a surface of genus at least 2. Genus of S is at least 2 in an interval. Yeah. So this is locally convex. This is locally convex. And then there is this unique extension to a manifold, which is still a product of S by -1, 1, but it's now a complete metric. Yeah. And this is what people call a quasifuchsian manifold. Okay. And then now the question I can ask, is, we have different situations. So one case would be this manifold here. Another possibility would be to say we consider the whole manifold, from -infinity to +infinity, so a complete manifold. And the third possibility would be something like this. I could have something like again, a quasifuchsian manifold containing a surface, let's say sigma minus, and then I consider everything up to +infinity, but starting from sigma minus. Those are examples of convex hyperbolic manifolds in the sense I'm talking about. Yeah. And then we can consider different types of boundary data. there are different possibilities. The first one is I can consider the induced metric on this surface sigma. Yeah. In that case, I can have, say, sigma minus here, sigma plus here. Another possibility is that I consider the third final form on sigma. Yeah. Another possibility, a third possibility, would be that I consider the conformal metric at infinity. And I can call this C. So I didn't really explain why, but it happens that for quasifuchsian manifolds, you know, the boundary at infinity is locally modeled on CP1, and there is a well-defined conformal structure here, which I can call C+, and here, which I can call C-. Yeah. It's a conformal class of metric. So when I say a conformal metric, I mean a conformal class of metrics. And then there is a fourth possibility, which I think already appears in the talk by Riemann. And the possibility is, you know, it's a special case of surface what one could consider, and that's what people call a convex pleated surface. So a convex pleated surface, I'm going to explain what it is, but I think Riemann already explained it quite well. So convex pleated surface in next, and then one can consider the induced metric, or the and then this is a hyperbolic metric, or the analog or the limit of free. And this, you know, free measures how the normal vector turns when you move around the surface, and this means that in this case, which it is a measured lamination L in a space of measured laminations, which is called ML of S. I'm going to explain this a bit more carefully in a minute. Yeah, I know it's a bit complex. So let me give you examples of things that you can do with those different invariants. We have quite a few answers in many situations here. And the first one is a theorem of Beers from the 60s. Yeah, it's a beautiful theorem. And the statement is following. It corresponds to what happens if you take C on both boundary components. When you have a complete quasifuchsian manifold, and you have two boundary components, and each has a conformal metric. Yeah? And then the theorem of Beers tells you that if you take C minus, C plus, the 2 points in the attachment space of S, there exists a unique hyperbolic metric, well, quasifuchsian, I should say, hyperbolic metric on this manifold S cross minus 1, 1, such that the conformal metrics at infinity are C minus and C plus. Yeah. Beautiful statement. It's more or less the starting point of this theory. And it has a number of beautiful applications in many different areas of mathematics and physics. Everything is clear? Yeah, don't hesitate to stop me by questions. Now, another statement, it's something I can call theorem 2, and that's something that Riemann already mentioned, that for which Labouré proved something in 1992, and I proved something in 2006. And the statement is again the following. Now we take two smooth metrics on this manifold. So H minus, H plus, the smooth metrics on S with curvature bigger than -1. Then there exists a unique convex metric on S plus -1, 1, such that 1 on D or plus minus M is H plus minus. Yeah? Yeah, sorry. Convex, hyperbolic. Yes. Yeah, thank you. I'm glad that someone is carefully listening. Thank you, Sergio. Okay, and then there is another statement, which is the dual to this, right? And that's 2 star maybe. That's from the same period. So now I'm take H star plus and minus the smooth matrix on S with curvature less than 1 and length of all closed geodesics bigger than 2 pi. And then again, there exists a unique convex hyperbolic metric on M, such that the third final form on D plus minus M is H star plus minus. Okay, that's something that we knew a while ago. Now, I'd like to tell you that there are more things we can do, and there are some things we don't know whether we can do. So, the first thing, okay, I forgot to say something very important. In the polyhedral case, well, now we know lots of things thanks to Riemann. So that's really, I'm going to refer to his talks. If he weren't here, I would actually explain this, but no, he already mentioned it, so I'm not going to repeat this. Yeah? Now, what I can say, and maybe I'm going to repeat also what Riemann said. Note that for, well, okay, suppose M in Mx is the smallest convex subset in the strong sense. So any geodesic with endpoints in M is really contained in M, strong sense, in Mx. Yeah? So this is really the sort of situation I was drawing here. You know, I take the smallest possible convex subset. And so Thorsten studied this convex subset a lot. And he realized it's a really beautiful object. It's called the convex core of M. And we denote it by C of Mx. So what happens for this convex core? Again, you know, we mentioned this. So the surface, you know, the boundary looks like a surface which is a bit pleated along some lines. So it's a bit like a polyhedron, but with no vertices, you know. Although it's a bit more complicated because the pleating locus, as mentioned by Riemann, can be very complicated. But still, you know, you have the induced metric, which is hyperbolic. So the induced metric has constant curvature equal to -1. And the third final form becomes this bending lamination L. Yeah? And so we have some results. So but some things are not known. So the question that was asked by Thorsten is whether any M plus M minus in the Tashma space of S, but now looked, I mean, seen as hyperbolic metrics, can be realized as the induced metric on the boundary of a convex core. And here, you know, existence is known by the people mentioned by Riemann. This would be Sullivan, a number of other people, Labourie, and so on. But existence is not known. Uniqueness, sorry, uniqueness is not known. This, by the way, shows why the polyhedral case is so tricky and so non-obvious. Even if you know the smooth case, it's not at all obvious to deduce the result in the polyhedral setting because you really have difficulties, and that's the reason we cannot yet prove uniqueness in that case. And also, the same thing can be asked for the bending lamination. And can any L plus, L minus in the space of measured laminations of S, which are reasonable, so I'm not going to tell you exactly what the hypothesis is unless you ask me, can be uniquely realized. And here, again, the existence is okay. And this is a result of Bounamont et al. But the uniqueness is not known. Okay, so those are questions. But now I'd like to play, okay, are there any questions on this? No? Okay, now I'd just like to mention that we can play some slightly different questions. So we can actually look at, situations where we looked at, what we can call mixed boundary conditions. And what I mean by mixed boundary conditions is we can take, let's say, the induced metric on one boundary and the third final form on the other one. We could take the induced metric here and the conformal class at infinity here. Or we take the third final form here and the conformal class at infinity here. And what I like to state is that basically those things all work, even in the more general setting of convex or compact manifolds. So that's a theorem that we proved with Qiyu Chen in I don't know when, maybe last year, maybe it was in 2022, I'm not sure. So I'm going to state it in the following way. For instance, let's H be a smooth metric on S with curvature bigger than -1. That I'm going to call this H minus, let's say. H plus star be another smooth metric on S with curvature less than 1 and length of closed geodesics at least 2 pi. Then there exists a unique convex hyperbolic metric on S cross -1, 1, such that the induced metric on D minus M is H minus, and the third final form on D plus M is H plus star. Yeah, that's one statement. And the same for, let's say, H minus and C plus. So here, I mean, we're going to get the induced metric and the conformal class at infinity. And the same also for H minus star and C plus. And here we get the final form and the conformal class at infinity. Yeah? So we can play those games. Basically we can say, I have this manifold. In this case, it's the product of a surface pipe R. And I want to prescribe what happens on the boundary. And I can choose to mix things. I can choose to have a conformal class on one boundary, induced metric on some other boundary, and so on. Okay. And last thing I want to mention in this, yeah. Yeah. So I'm going to tell you exactly this because in the case where actually there is something slightly more general known, if you take, a situation where you have one pleated surface here and one smooth surface here, and I think what you are asking would be a limit where the smooth surface goes to this boundary, and the answer is that, so it's a recent result of Abderrahim Mesbah, who is doing a PhD with me. So he proved exactly what you ask, but only existence, because uniqueness is tricky for the same reason as usual. So let H be a smooth metric on S with curvature less than 1, bigger than -1, sorry. Let L be L be a measured lamination on S, and then there exists a convex hyperbolic metric on S cross -1, 1, such that the induced metric on the upper boundary is H, and the lower boundary is splitted with splitting lamination L. So in fact, if you prescribe L here and the induced metric here, it was a result of Qiyu. That was so that was a special case, right? Qiyu. It's an unpublished paper, in fact, but that was the case. And then it also works. I'm not going to write the full statement. Also for the third final form or the conforming class at infinity instead of the induced metric. Now, uniqueness is going to be tricky in this situation. I think, again, the same reason applies. Maybe for rational lamination, we could get uniqueness. That's probably going to be possible. Okay. Any questions on this? Indeed? Question for Roman. You know about it? I think it's, yeah, I also think it's not known. But yeah, hopefully we could expect something. Okay, so how long do you have? 5 minutes? Okay. Let me go then. I'm not going to do everything I wanted to do. Let's go to the universal setting. So what I mean by this is what happens if you take this M and you look at the universal cover of M, So what about M tilde? And basically, if you think of it, you come to the following conclusion. We have this beautiful theorem of Alexandrov, sorry, for the right problem. And the Alexandrov statement concerns closed convex domains. Now, you could say something else. You could say, I'm going to take a domain in H3, which is, let's say, bigger than this. It's going to be convex, but not necessarily closed. I mean, not closed. Unbounded convex domains. So the question is, how can we determine an unbounded convex domain omega in H3 from boundary data? So that looks like a very natural question. And well, unfortunately, I have very partial answers only. And what I'm going to say is I'm going to tell you something that I think could be true in some form. And then I can tell you what we know. I probably won't have time to tell you much about what we know. The statement I have in mind is the following. So first, I like to make a remark. if I have this omega included in H3, I can look at the inclusion of the boundary of omega. So I include the boundary at infinity of omega in the closure of H3. Let's say in the Poincaré model. That's the simplest thing to do. Yeah? And then the boundary of omega bar is equipped with a conformal structure. So I can basically identify it with CP1. And moreover, there is this U inside the boundary of H bar, which is open, which corresponds to the boundary of omega within the boundary of omega bar. Yeah? Basically, it's a part of the boundary which is contained in H3. And then I'd like to ask the following question, and I think the answer is going to be no in general, but I hope that with some additional conditions it's going to be yes. So I'm going to take the following situation. Let U be domain in CP1. And I'm going to write U as the union for I in some set of UI, which are connected components. Then for each U, for each UI, for each I in big I, I'm going to choose either HI, which is a smooth, so it could be non-smooth, but let's say a smooth metric, a conformal metric, so conformal to the conformal class of CP1 on UI with curvature bigger than -1, or HI star, a smooth conformal metric on UI with k less than 1 and this length condition. Then the question is there a unique omega in H3, convex, unbounded, of course, such that, so as we say, the boundary of omega bar is identified with CP1. In this identification, the boundary of omega is identified with U. And 1 on UI is HI, respectively. The third form on UI is HI star. Yeah? So do we have 1 more minute? Okay. Yeah, equipped with a conformal structure, which makes it, identifies it with CP1. Well, basically, it's the in the manifold there will be, let's say, if at infinity there is this conformal structure at infinity. Yeah, you will have ways. You have to ways to reconnect those things. It's clear that it's not completely obvious. In fact, you're right. Okay, so what we can prove, I mean, there are different things. There is a theorem that we proved with Francesco, Monsante, Danziger, Jeff Danziger, and Sarah Maloney in 2021, I guess. So the answer is yes, in a very special case. So if U is CP1 minus lambda, well, lambda is a quasi-circle, and I take, so the complement will be made of 2 quasi-disks, and H, or respectively H star, has constant curvature, on the complement of U, on U, yeah? So, sorry. And this is not, yes, it's only existence. We don't know uniqueness. And okay, there is another more general statement, but I'm going to stop here because it's time for lunch. So thanks for your attention. And yeah. Yes. So to be precise, I think this statement it's the upper statement is proved in that generality. I think the statement by Abderrahim, he only proved it in the quasifuchsian case. I think it should probably work also in the general case, but he only looked at the quasifuchsian case. Yes. Yeah. Yeah. Ah, yes. Yeah. So I think what you, if I am trying to think of what you say, that's an interesting remark, because even if we don't talk about Riemann's results, sorry, Riemann, we can talk about the the ideal polyhedra. For ideal polyhedra, you have those vertices at infinity, and you can ask, is it true that this statement is a special case of this question? Yeah. So I never thought about it in that way. But yeah, I think that's true, actually. That is a special case. Because then we just ask the metric on the boundary of U. Now, U is a complement of a bunch of points. And we can say, for the induced metric on the ideal polyhedra, we can say, we fix the metric to be the conformed metric, the unique conformed metric, complete conformed metric, which is hyperbolic on the complement of the points. And then we recover this result of Riemann on the induced metric on the ideal polyhedra. If we look at the angles, it's probably going to be a limit case. Yeah, thanks. Alexander, yes. Yeah. Riemann's one? Yeah. Yeah. Yes. Yeah. So let me try to repeat if I understand well. You say, I take a metric of, let's say, curvature bigger than -1. I get a convex body, and I recover another metric, which is a third Fernand form. Yeah? And then this is a metric of curvature less than 1. Okay. I don't know. I don't know. There are different situations where you, in this case, where you can associate to those geometric constructions some dynamical systems. Something, I mean, I think the simplest case you can think of is you take this, statement we're talking about the induced metric on the boundary of this polyhedron. Then, applying the Riemann theorem, we get an ideal polyhedron from a conformed metric. And then we get another conformed metric at infinity, which is the one of the complement of the points. And then we can repeat this, for instance, and ask, whether this dynamic system is going to converge, what's going to happen. I have no idea. I think that's a really cool question, in fact, but I don't know.